Okay, welcome to Learning Target 6. This is the last learning target in the discrete distributions unit. So big thing here is choosing the correct distribution. The homework relies heavily talking about binomial, hypergeometric, when to use which. Well, we won't spend a lot of time looking at examples, but we will look at some here. But we want to talk about like the key differences, mainly between binomial and hypergeometric. So that's the point of today. So, if you're conducting a game that uses a deck of cards, you can make any kind of rules you want. What would have to be true for the probability to be calculated using the binomial, hypergeometric, or uniform? The way I chose to answer this question is just to give an example, and I'm just going to talk about what would have to be true. So for binomial distribution, that's something where like you've got the probabilities the same for each one. You've got order mattering, and you're counting the number of cases. And so here, like an example would be if you draw 5 cards with replacement, the probability of a different number of spades. So first card could be a spade, but the last card could be a spade as well. And so if you want the probability that you had 1 spade, you'd have to count the number of cases. There's 5 cases there, where you've got 1 spade and then the rest non-spades. But the key here is the replacement. The probability is the exact same every time. So that actually has to be true to be using a binomial. The probability of a spade is the exact same every time. 13 out of 52 or 1 out of 4. Hypergeometric, an example would be draw 5 cards without replacement. Probability of a different number of spades. So we use the exact same example, except we recognize that if we don't replace them, if we just have a hand of cards, what's the probability that you have a different number of spades? You might ask about order here. It's not so much the order, because like if order mattered, it would still be a hypergeometric. In general, we say order doesn't matter, but like we would get the same thing if order did matter. Don't worry so much about that. In general, we just think of it as a situation where we have combinations. But the probability changes. We're not replacing the cards. So that's going to be a hypergeometric. And the last one's uniform. And so my example for uniform is if you draw 1 card. I don't know why I said with replacement, but draw 1 card and the probability of getting a different suit. So you could have a game. Each of these you could have a game where you get prizes depending on the number of spades, and uniform could be you get a prize depending on what suit, a different prize depending on what suit you get, and that would be a uniform because the probability is the exact same every time. So you'd have to have something where every different outcome has the same probability. Binomial hypergeometric, the outcomes are 0 spades, 1 spade, 2 spades, 3 spades, 4 spades, or 5 spades. Each one of those outcomes has a different probability, depending if you're binomial or no matter if you're binomial or hypergeometric. Uniform, you have to have the same probability every time. So learning target actually focuses more on hypergeometric versus binomial than uniform, but I know that the hypergeometric distribution is used when trials are dependent and limited, and the binomial distribution is used when trials are independent and unlimited. This limited, unlimited, this was my idea, like to think about maybe another way to help us kind of understand it. It's not so much in the case where like in the example you had five cards, so we're drawing 5 cards. So I'm not saying like that's unlimited. I'm saying like the opportunity to draw more cards is unlimited, and we'll talk about that. I can choose which distribution to apply in given situations, and can give scenarios that are binomial and that are hypergeometric. So there's what I'd ask you, like just like in the warm-up, to give me a scenario where it's binomial versus hypergeometric. The key here is independent versus dependent. We talked about this in the first unit. So there's a slide on conditional probability, and so that was, largely ironed out by a tree diagram. So, or really just common sense. So if we weren't replacing cards, the probability of drawing a spade would be 1 out of 4 the first time, or 13 out of 52 the first time, and 12 out of 51 the second time. Probability the second one is a spade. It depends on what happened the first time, so we call that dependent. That's the same thing for combinations. So binomial is actually independent. So you think about things like rolling a coin, flipping a die. Flipping a I have such a hard time with this. Flipping a coin, rolling a die. These are independent trials. It doesn't matter if you rolled a 6. You have the same amount of probability of rolling a 6 again, 1 out of 6. It's kind of hard to understand, but it is an independent trial. Okay. Trials are not impacted by previous trials. If you flip 2 heads, see, I know about flipping. I got it right there. This does not change the probability of flipping the third coin. It is known that if it is known that 2% of products are defective, each new product has a 2% defective rate, regardless of what has been found in products that were just tested. I mean, and that's the idea here. Like, just because you already got 2% in this batch doesn't mean the next guy is not going to be defective. It's 2% altogether, and so. And this is where we'll keep talking about this unlimited, limited thing. Hypergeometric is dependent trials. So as items or people are picked, the likelihood of a similar item being picked changes. So if a spade was picked, the likelihood that the similar item is picked changes. It doesn't even really have to be a similar item, but the likelihood of any item changes because you're not replacing. So it's just this idea of like not replacing, and that the trial before impacts the next trial. Cards without replacement is the most common thing we look at. Picking a committee of people, obviously, like, one person can't be picked twice, because if they're in the group, they're in the group, and so that would be a common example of hypergeometric. Limited versus unlimited trials. So I just want to, this is just to give you another idea here to tell. But this is kind of helpful for me, and so I'm just trying to articulate that. And so in a binomial distribution, there's technically no limit to the number of trials that are possible. So if it's 2% defective, it just means if we keep getting parts, we're going to keep producing 2%. So we're just saying, if 1 million parts go on, and we just keep doing it. And so we could pick 1,000 parts, we could pick 1 million parts. Law of large numbers has a big role to play here, but there's technically no limit. It's an idea that you could flip a coin 2 times, you could flip a coin 10 times, 100 times, and you could have a binomial distribution based on that. Hypergeometric distribution, there is a limit to the trials you can take. Now you can take 5 cards a whole bunch of times, but it's just that idea that once you take 5 cards, you could take 6, you could take 7, but you couldn't take 53 cards. So there's kind of an upper limit, an upper bound of what's happening. Often we look at something like roll up the rim to win as a binomial distribution, because the probability that we think of these cups as unlimited. There is technically a limit to them, and it can fit a hypergeometric distribution, but it's just much easier to approximate with a binomial distribution. And certainly if you think about, what's the probability I'm going to win a car if there's only 2 cars out there and they're already gone? It's certainly not the same as it used to be. And so we think maybe it's hypergeometric. So if you're not replacing the outcomes, you will run out. You can't pick more than 52 cards, as an example. And that's basically it. The big thing here is you just practice. These are really good questions to go through to make sure you really understand the difference between, and they ask about uniform as well, but it's just make sure you really understand the difference between these distributions.